In question 5, we are asked to represent a given circuit in form of matrix. So we first look at all the possible outputs for the various inputs and try to construct a matrix from them. So the possible inputs are 0 0, 0 1, 1 0, 1 1. In this circuit, we can see that there are two conditional NOT gates, where in the first condition NOT gate we have the first qubit as the control bit, and in the second C0 gate we have second qubit as a control bit. So on application of first C0 gate, in the first C0 gate we can see that our control bit is the first qubit, as wherever we have first qubit as 0, the second qubit doesn't get altered. So we can write those states as it is. And wherever we have first qubit as 1, which is control bit in this gate, the second qubit gets flipped. So these states become this way. And in the next, after applying next C0 gate, in this C0 gate we can see that second qubit is the control bit and first qubit is target bit. So wherever we see second qubit as 0, we don't alter the first qubit. So wherever we have 0 qubit, we are not going to alter the first qubit. And wherever we have control bit as 1, we need to flip the target bit, which is first qubit. So how do we construct matrix from these results? Before trying to construct matrix, I would like to show you the required information which we have constructed previously, which we see that qubit 0 0 is 1 0 0 0 and qubit 0 1 is 0 1 0 0. We can see that these 4 states can be seen as basis, orthonormal basis for a vector space of dimension 4. So here we see that these 4 states form basis for a vector space of dimension 4. So their corresponding outputs become the columns of the transformation matrix. So matrix is just which is concatenation of columns of output of these states. So the columns are when M gate is applied on 0 0 and M gate applied on 0 1 and M gate applied on 1 0 and M gate applied on 1 1, which are 0 0, 1 1, 0 1 and 1 0, which are actually so the columns of matrix are outputs of the transformation when basis vectors are used as inputs. So, we have these 0 0 1 1 0 1 1 0 which are already computed by us in the starting of this assignment, which are put in the matrix as columns. So, the answer to the question is option B. In the question 6, we have a problem based on teleportation circuit given in lecture 9. The question asks, the teleportation was done with Alice and Bob sharing the Bell state 1 by square root 2 0 1 qubit minus qubit 1 0. Then what action should be taken by Bob to generate the state alpha 0 plus beta 1 if Alice's measurement gives the state 1 0. In the lecture 9, we see that Bell state shared is different from the question. So, we proceed from the initial step and we try to decide which is the transformation that should be used by Bob. So, the Bell state shared by them is 1 by square root 2 times 0 1 minus 1 0. So, the first operation performed by Alice is applying a C0 gate on the state the first step need to perform is C0 gate should be applied on the state alpha 0 plus beta 1 which is multiplied to the Bell state they shared. Don't confuse with the notation I have used. The thing I am trying to convey is we need to apply C0 gate on this state where the first qubit is control bit and second is target bit. So, let us expand this term which is one by square root 2, take it common and it's multiplied with, and first separate 1 by square root 2 term and then group them terms based on the coefficients. Now, we multiply alpha 0 with this thing. And the terms with coefficient beta are so when not gate C0 gate applied, the first qubit is control and the second qubits are target. So, resultant state after applying C0 is wherever we have 0 as a control bit, target bit does not get altered. So, the output is after applying C0 gate, we apply H gate on first qubit. Applying H gate on qubit 0 gives the output 0 qubit 0 plus qubit 1 divided by square root 2, and application of H gate on qubit 1 gives us qubit 0 minus qubit 1 and the normalizing constant 1 by square root 2. And now we apply H gate on first qubit. The first state we have in the previous expression is qubit 001. So qubit 001 we have previously. So let us write the previous expression completely. This state can be written as H gate is being applied on the first qubit, this gets transformed to qubit 0 plus qubit 1 divided by square root 2, and this can be again written as so. Similarly, we do similar calculation with every other state, and as a single state, from a single state after applying H gate, we have got combination of 2 states. As we have 4 states here, we will get total 8 states in the final resultant state after applying H gate on the first qubit. So after applying H gate, the resultant state is half times the terms with alpha coefficient are 001, 101 minus 010 minus 110, and the terms with beta as coefficient are and if you see carefully, we can written this expression also as something by separating first 2 qubits. Now if you look at these underlying states, we can write them as we have written these common qubits separately, and then we can multiply it with the state alpha 1 minus beta 0. Similarly, grouping other pairs, other similar pairs, we obtain So this is the final state we obtained after applying C0 gate and H gate. Now we are given that Alice measurement is 1 0. So the state Bob has is but the required state to be generated is so by mere observation we see that the coefficients gets flipped, that is like the qubit 1 has coefficient alpha, but here the qubit 0 has coefficient alpha. So you can clearly see that on application of a NOT gate we can obtain the required state, and we also know that a NOT gate is same as X gate. So we conclude that Bob has to apply X on his qubit. So the answer is option A. Now we look at question 7. Question 7 is a simpler one where we are asked to compute the action of a gate on the given state qubit 0 0 minus qubit 1 1 divided by square root 2. First let us compute the matrix representing this gate. The gate given is this thing, which is equal to matrix product with. So remembering this matrix is very essential thing while performing calculations. So we obtain which is equal to, so this is the gate we are applying on state 0 0 minus 1 1 on the normalizing factor. We have already computed these states, which are which is 1 by square root 2 times 1 0 and the qubit on which we are going to operate this gate is, so we just need to perform matrix multiplication now. The gate which we obtained is previously multiplying this with qubit, which gives the first column multiplied with the vector gives us 0, and the second row multiplied with the vector gives 1. Similarly, we obtain the final output as 0 1 1 0 having a factor of 1 by square root 2. So we can write this as from our calculations before starting assignment, we observe that this vector is same as 0 1 and this vector is same as 1 0. So the final output is qubit 0 1 plus qubit 1 0 divided by square root 2, which is option C. Question number 8 has considered a state which is given there, and we are asked to find the probability of measuring the second qubit as 0 the preceding measurement of the first qubit yielded the state 0, we are asked to find probability of obtaining this state when we are given that the first qubit is already 0. After a measurement is done on qubit 0, this state collapses to and now we are asked to measure probability of obtaining second qubit as 0. That is, we are asked to find probability of obtaining this state when the given quantum state is a linear combination of these two states. As we know that probability of obtaining a state is proportional to square of its coefficient. So, probability of obtaining zero zero one state is A is some constant. It's not some constant, it's a normalizing constant. Normalizing constant. A is a normalizing constant. And also we also know that the sum of square of coefficient should be 1. So, we obtain A square as 1 by 12 square plus 3 square. So, required probability is 12 square times A square, which is equal to 12 square divided by 12 square plus 3 square, which is 144 divided by 144 plus 9. Observing that 144 is 16 times 9, we can cancel out 9 in numerator and denominator, and we obtain, which is 16 divided by 17, which is option D. And now we look at question 9. Question 9 is also simpler one, which is based on matrix product. Here we are given matrix product and the vector, and we are asked to find another vector. We are given the product is 1 by square root 10 times minus 2, 1, 2 and minus 1. And we are also given that state A is 1 by root 2 times minus 1, 1. So, let us assume that state B is, say it is C, D, and C, D are some constant, C, D are variables here. And now we compute equal to which is so on comparing these two states, we see that minus C by root 2 is minus 2 divided by root 10 and minus D divided by root 2 is 1 by root 10. And comparing these two terms with these two terms respectively also gives us the same relations. From these two equations we see that C is 2 divided by root 5 and D is minus 1 divided by root 5. So state B is 1 by root 5 times 2 minus 1. So the correct answer to this question is option B. Till now we have seen single correct answers where we have solved many problems on quantum gates and manipulating quantum states and teleportation circuit. So in the next video we will be seeing about multiple correct answer type questions.